Greetings and welcome to a new video about another electric circuits problem. We have in this case the first example about our superposition principle. We will discuss this in this example. As we did in the previous videos using nodal analysis and also the mesh current analysis, we will look at the calculation step by step and also verify these in SPI simulations. And we consider only DC circuits for now. Okay. This is the circuit we have given. This circuit has two voltage sources, DC, 2 volts VA and 5 volts for the VB, and we have three resistors, R1, R2 and R3. We would like to use the superposition principle to calculate, so using the principle of superposition, calculate the current through resistor R2. That's actually shown here. So I have chosen the current direction already, giving the plus and the minus signs. This is what we want using the superposition principle. So how do we work it out and what are the steps? So let's look at the solution step by step. We have two sources in this case. So for a circuit having more than one source, current or voltage, or that doesn't matter, in combined fashion, superposition principle can be very handy. So you can actually decompose a very complex or large problem in smaller problems and add them up. That is actually the whole business of superposition principle. It only applies, by the way, for linear systems or linear circuits, so you cannot apply this for nonlinear systems or circuits. The step one is the following: keep only one independent source at a time in your circuit. So if you have a 2, you keep only one of them and you disable actually the others. So in this case, disabling means actually make it inactive. So if I keep VA active, so let's say only VA active, that means VB is shorted. Why is this shorted? Because this is assumed to be an ideal voltage source. An ideal voltage source will have a zero output impedance. If this was a current source, I will have it open, because then the current source in the ideal fashion has an infinite input impedance. So that's actually the procedure to, let's say, make it active or inactive for the voltage and the current sources. So in summary, you make a short when you see a voltage source if you make it inactive, and if you see a current source you want to make it inactive, you make it open. Now only VA active, then the circuit becomes as follows. So we have the VA, still the resistors are there, and you make a short here, so the VB is just shorted. So that's gone. So you actually have now a different circuit. Now we can simplify this, because we like to calculate this current. And that is now only due to VA. So this current here is not anymore I2, but it's I2 due to VA. So I just name this in a different way. So I do I2 comma VA, just because of that VA source here. Now, how can we do that? There are many other ways to do this. I have chosen to combine R2 and R3 and make first this node X. That will be helpful shortly. So I combine these two resistors and then get actually a series combination, and it will be, of course, handy to work out later. So combining these two, R2 and R3, so actually this dashed pink region, that will give me a parallel combination of R2 and R3. That's actually shown here. So parallel combination of two resistors can be also written in this formula form. So R2 times R3 divided by the summation of these two resistors. Now you have a 20 and a 60 ohms for the R2 and R3 divided by the summation. You will get exactly 15 ohms. So 15 ohms can be now used instead of these two resistors in parallel. So the circuit then becomes, actually this one. So it is R1 in series with Rx. We have just named them Rx. And this is now the simple circuit we can use to calculate the voltage at node X. The node X is here designated to also determine the voltage across the resistor R2, because once I know the voltage across Rx, I also know the voltage across R2 because they are parallel. So when you do that, you have also your voltage. And if you know your voltage, you can use Ohm's law by dividing that voltage over this R2, and you have your current specifically only for this circuit. So using the voltage divider rule, you will actually get this expression. That means Rx over the summation of these two resistors times the VA, and it will give you the Vx, actually is the voltage across this Rx. It will be then 15 times 15 over 10 plus 15, so that's actually the summation of this one, times 2, that's the voltage source value for VA, and you will get 1.2 volts. Now we are now very close, because I would like to have this current due to that VA. Now I have its volts also, so V2 is also equal to Vx. So we can say, then we have the I2 comma VA is equal to Vx over R2. That is 1.2 over 20, and it will give you 0.06 amps or 60 milliamps. Okay, now let's keep it here for a reference and now move on to the next one, because we also have the VB. So only VB active, then that means VA is now shorted. So the circuit becomes like that. So this is only present, so we leave actually only VB in the circuit, and you see that it's shorted. Now you get actually the similar procedure. You get this current here, but now it is due to VB only. And again, I will designate here another node that I also name it differently. It is not the same node, also not the same resistance. So I will call this Y. Now I have another situation. So combine R1 and R2 now, and also make that series connection for R3 and the new resistors we will get. So if I now box this, that blue part, that will be then the RY, which is then the parallel combination of R1 and R2. R1 and R2 are given 10 and 20 ohms. Now if I do 10 times 20 over 10 plus 20, you will get 20 over 3. It's not exact. So this is the exact, I mean, if you calculate this, you won't get a nice number, so I will keep it as it is. Okay, now this is now for this RY. We can move on and then say, how is this circuit now simplified in this form? So you've got R3 and a VB in series with this new RY. And the current here, it will be then actually also shown here for this orientation. The voltage is now actually also calculated using voltage divider rule, using this. So VY is equal to RY over the summation R3 plus RY times the VB. So we have now everything. So 20 over 3 over 60, because that's 60, plus 20 over 3 times 5. Now, the benefit of having this in exact form is that you get now here an exact value also. Otherwise, if you use this, let's say, rounded off version, you will get also a nice number here, and you will get also errors at the end. So keep it as exact as possible, and it will get 0.5 volts for the VY. Then we have the following. The I2 due to VB is now similar form. This voltage here at this node Y is also the same for this voltage and also for the R2, because they are parallel. Then we can say 0.5 over 20, you will get 0.025 or 25 milliamps. Now step 1 is done. So we've actually two separate steps in step 1, one for the VA and one for the VB. Now we need to combine the results, the separate partial results, to get the total solution or the net effect. Now that means actually the following. Because it is a linear circuit, we can use the superposition principle as follows. We can say the result from the first circuit, that's the current, plus the result of the second circuit from the current, you add them up. Just add them up. So plus, and you will get 0.06 for the first and 0.025 for the second, and you will get 0.085 milliamps, 85 amps, and it will be then 85 milliamps. And that is really the answer for this I2, for the current through resistor R2. Okay, now let's give it a summary. This was a circuit we have given. This is what we had, and then we actually transformed this first by shorting this, so disabling actually everything except this VA, and you got this circuit. You also did that for the other one, so you only kept VB active and you got this circuit. Now we also made that circuit simple, so in order to calculate Vx, Rx is calculated first, Vx, and also then the I2 due to that Va. In a similar form, we did this for this circuit. So I go actually a little bit faster to summarize this and also simplify this circuit, and then you get also Ry and Vy, and then also calculated the I2 due to Vb. Now you get the 60 milliamps for the left side and then the 25 milliamps for the right side. Now the total solution was the summation of these two, and then we will get 85, let me get back, 85 milliamps. Now, let's also look at the simulation results, because this was the total solution, and this was a circuit, and this is the circuit I have drawn in the simulator. You can see the 10 ohms, 60 and a 20, and 5 and a 2 volts for the voltage sources. And this is what we have calculated. Let's check that. Now, when you do the simulation and DC analysis, you can generate a table, and now you can see here, this part, you can see I underscore R2. That is 85 milliamps. It is exactly what we have calculated. It's actually between 2 and 0. It's actually shown here between the parentheses. That's the voltage we have now, or I mean the current we have calculated, and it's also the simulation, so it is exactly correct and it is verified. You can see actually more in this table. You can see also the voltages for each resistor. So that is just an extra information. So we can say our calculations are verified by our simulation. Let's now also jump to the actual simulator, the SPICE, and also show you how you do that in the simulator and also how to generate this table. So let's jump there and then close this session. All right, this is now the circuit for our example. I can also show you the units, it will be helpful. So 2 volts, 5 volts, and also 20, 10, and 60 ohms for our resistors. Now, how do I know the current now here? It must be 85 milliamps. We have determined that. So what you can do analysis, DC analysis, and go to calculate node voltages. And then go with your pen directly here. And you can see it's current 85 milliamps and also its associated voltage 1.7, but it wasn't the question. What you also can do is to get you more information is generate a table. So you go to analysis and DC analysis and then go here, table of DC results. You get then a lot of information, more information here, and you can highlight actually also the R2, and you can see directly in red the current and also the associated voltage for this element R2. You can also do it for R1 and also for R3 in a similar form. You can also look at the node. So if I click on this with my pen, you can see that it is also 1.7 volts. So these are all possible, let's say, analysis you can do using the simulator to check your calculations. All right, this is then for this example, the first example about the superposition principle for this circuit having 2 DC voltage sources, both are ideal, and 3 resistors. We will continue in the next examples, discussing more complicated circuits to illustrate the concept for this superposition principle method. So if you have any questions about this example, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.